Okay, and we're live. So we're going to talk about reaction mechanisms. Reactions happen. We go from reactants to products. The kinetics is the rate of that. But what we also find in reality when we monitor these reactions is they don't just go from reactants to products. Usually we form some intermediates. So we might start to lose one bond, reform another, start to get partial bonds. So there's actually steps that happen on the way to that final product. And those are the mechanisms. It might be just one additional step, might be 2 steps, 3 steps. So we need to figure out what are those steps, how many steps are there, and how do those individual steps actually affect the rate? Because if we know that, we could figure out how to manipulate this reaction. What can we do to speed it up or slow it down? Are there certain catalysts that will be good or bad or whatever? So here we have our overall reaction. There's our reactants going to products. This is actually a 2-step mechanism. So what you see happening here is we're forming this HI intermediate. And then we have the second step where the intermediate is used up and we proceed to products. And you can see if we add those 2 reactions together, we should end up with that overall reaction. So these are called elementary steps. So how many elementary steps can we break this overall reaction into, or how many actually occur? So like I said, here we are adding them up, canceling these out. HI is a product in step 1, but it's used up in step 2. So that's what we would call, like I said, an intermediate. And lots of different reactions have intermediates. Knowing what that intermediate is, like I said, will allow us to potentially affect or speed up this reaction. And this will also allow us to verify what is the overall rate for this reaction. So we have this term molecularity. This essentially just means how many particles are involved in that reaction. So unimolecular step involves 1 particle. So that's probably just a decomposition. Bimolecular would be 2 coming together, and termolecular would be 3 or more particles. And these are actually very, very rare. Because if you think about the likelihood of multiple particles coming together in just the exact right conformation at the exact right moment in time, it's more and more rare. So each of these each of these elementary steps are going to have their own individual rate laws. And if the elementary steps are correct, if they're the ones that actually occur, we should be able to add up those elementary steps and add up those or combine those rate laws and get the actual rate law for the reaction. Now, unlike the actual reaction where we cannot just guess what the rate law is from the reaction and from the stoichiometry and all that, we can do that for elementary steps. So if we're talking about those individual steps for the reaction mechanism, for those we can look and say, okay, this is going to be the reactants, H2 and ICl, and we're just going to be able to take the stoichiometry directly. So this reaction is going to have some rate, K1, because it's the first step, and the 2 reactants, H2 and ICl, and they're going to be raised to the first power because that's the stoichiometry here. And the same thing for step 2. Now, again, we can't do this with the overall reaction. That has to be determined experimentally. But we can do this for the individual steps. And then what we could do is add these reactions. If we add the reactions, we would multiply the different rates. And if that came out to the same thing as our overall rate, then these elementary steps should be correct. This prediction of how many steps are they and what are they should be a correct prediction. So this just shows some of the molecularity, unimolecular, bimolecular, termolecular, and how that rate law would look. And again, because these are elementary steps, we can take that rate law directly from the reaction and the stoichiometry and figure out what that is. But that is not the same thing as the overall rate law, and the overall rate law always has to be determined experimentally. So what is the rate law for the elementary step? So there's our keyword, elementary step. So from that, we can just use the equation. And it should be those 2 reactants, Cl and chlorine and carbon monoxide. And they each have a coefficient of 1 in front of them, so they'd be raised to the first power. So that should be D right there. All right, so this brings us to the rate determining step. So we have a couple things. We're gonna, when we set up a reaction, like I said, we may have a way to monitor that spectroscopically, chromatography-wise, whatever it happens to be, that sort of allows us to hypothesize how many steps are there, or is there an intermediate? Do we see this compound being formed at some point in the reaction and then starting to disappear like an intermediate would? So we're going to be able to guess, or like I said, hypothesize. This is 2 steps, or these are 3 steps. We're forming this intermediate, or this thing is acting as a catalyst. And then what we want to do is set up those reactions, set up what their rate laws are for the elementary steps, and then confirm, do those elementary steps, do their rate laws add up to the overall rate law? If the answer is yes, then our hypothesis is very likely correct. We also then have to determine what is the rate determining step in these elementary steps, because that's going to affect how we sum or multiply these rate laws to get to the overall order. So the slowest step in any mechanism is the rate determining step. We may find that we have 3 possible elementary steps, and 2 of them occur very, very quickly, and 1 occurs very, very slowly. So that's going to make our bottleneck. That's going to determine how quickly the reaction overall actually happens, and that's why we call it the rate determining step. The example they give here, if you start closing off lanes, right here where you go from 3 lanes of traffic to 1 is going to pretty much affect how quickly or slowly is traffic going to be able to move, and how easily can these cars merge, and how many cars have to compress from 3 lanes down to 1. The rate determining step is essentially the same thing. So here we have our overall reaction and the actual observed or experimental rate. We hypothesize that this occurs in 2 elementary steps, the first one being this, forming this intermediate NO3, and then the second step using that up and taking us to products here. And we should be able to sum up these 2 reactions, and if we do, we see this NO2 here cancels, the NO3 cancels, and we have NO2 plus CO goes to NO and CO2. So it matches the reaction above. And you'll notice we have the rates for each one of these predicted solely from the equation. But they're telling us, or we're hypothesizing based on however we set up this experiment, that this first step is slow and the second step is fast. So that means this is going to affect the rate of the reaction. We can only make that NO3 and that NO so quickly. And the second reaction cannot proceed until we have those reactants. So that's going to be the rate determining step in this case. And we'll look at, when we know how many steps we have and we know what the rate determining step is, how do we then get to the actual rate expression or rate law for the entire thing? If the first step is slow, we can ignore the second fast step, because as soon as these products are made in the first step, the second reaction is immediately going to proceed. So in that case, if the first step is slow, if the first step is rate determining, then the rate law that we get from the first step should be the same thing as the observed rate law. And in this case, they are. So this prediction is probably correct. So like it says, the first step is slower than the second step because the activation energy is higher. So we've seen these plots before too with activation energy. And usually it's just a single hump and then it goes down to products. Of course, the reality is a lot of times when you observe this, this will give you tips or hints that yes, there's multiple steps. So this is one of our transition states, or forming our intermediates and going then finally to products. And you can see in this case, we know the first step is slow compared to the second because the activation energy is higher. This has the larger barrier slowing us down before we can proceed to products. So then validating a mechanism, like I said, so 2 conditions must be met. However many elementary steps we predict, 1, 2, 3, we should be able to sum them up and get to the overall reaction, which has been the case in all the examples we've looked at so far. And lastly, the rate law predicted by those elementary steps should be the same as the observed rate law. So depending on which steps are slow and fast, how do we add these? What rate laws do we need to sum together from how many of those steps? When we do that, if it matches the observed rate law, then we validated that mechanism. So I'm going to stop here on this video. Maybe, there we go. And next video, we'll look at what do we do if we have a fast initial step and a slow later step.